Hello, my name is Judith Evans. I'm going to tell you a little bit about the IC cold store audits. In particular, I'm going to talk about one of the audits we carried out in a chilled dairy store. If you want to find out more about how we carried out the audits and results from all the audits, there's another webinar which deals specifically with these issues. The dairy cold store that we audited was Yo Valley. This is an organic yogurts, desserts and milk producer. It's a family business that was set up in 1974 in the UK, and we audited 3 cold rooms which were all used for storage of chilled products. How did Yo Valley get involved in the audits? Originally they took part in the benchmarking survey and volunteered for an energy audit. They actually came out quite reasonably in terms of their efficiency in the benchmarking survey. But because the company has a big emphasis on efficiency, sustainability, recycling and their organic credentials, they wanted to see if they could actually improve the efficiency of their cold stores, and so they were very keen to volunteer and become involved in the audits. At the Yo Valley plant we audited 3 cold stores. The data recorded was over approximately a 2-week period where we recorded energy consumption, information about the operation of the refrigeration system and the ambient conditions. And as part of that we found a number of ways to save energy, which I'll talk about as we progress through the presentation. In terms of the heat loads from the audit, we looked at the heat loads on each of the stores, in terms of things like the transmission, the defrost, the lights, the product, infiltration, the evaporator fans, forklift trucks, people, and infiltration from battery charging and doors. As you can see, the 3 stores, although they were very similar stores, they were all built at the same time, built by the same contractor and built to a similar standard. They all had different issues. In particular, you can see in store 3 the lighting load is particularly high, and this was because there was more lights in store 3. But it's very interesting to see the differences between quite similar stores, and to not make the assumption that just because a store looks quite similar, it is actually very similar issues. In terms of the lighting on the cold stores, we looked at the impact of installing LED lights. You can see that on store 3 this had the largest impact, mainly because this had the largest lighting in the first place. And you can see we could reduce energy in the cold stores by between 12 and 25% by installing new lighting. And this was shown to be a reasonably feasible proposition with good paybacks. We also looked at heat leakage. In 2 of the stores in particular, they charged the forklift batteries within the store itself. If you charge batteries within a store, you must have ventilation for safety reasons, and so there's a heat load as air is drawn into the store and extracted out. Originally, the areas that were used for battery charging were actually isolated, and they had rapid roll doors on them. However, over time these doors had become damaged and were no longer used. We calculated that by not using these doors, this increased energy by about 11%. And so for a relatively simple maintenance repair, we could reduce the energy used by the store quite considerably. We also found issues around the defrost optimization. We found quite often that not all evaporators were actually used to maintain the temperature in the cold store, and even if they weren't being used, they were still being defrosted. And there was 20 kilowatts of electrical heaters in each of the evaporators, and the evaporator defrost was run for 30 minutes 4 times a day. With the evaporator defrost you get a 2-fold hit. Not only are you paying for the energy for the defrost itself, but you're also paying for the refrigeration system to extract the heat from the room. We suggested that you could cut the number of defrosts quite considerably within the stores, or even move to a passive or off-cycle defrost system. We also found issues with superheat control. We found that the expansion valves, which should control the liquid feed to the evaporator, weren't controlling to the required 3 to 4 degrees of superheat. We found the evaporators weren't therefore being used effectively, and this reduced the evaporating temperature, increased the compressor run time, produced uneven ice formation on the evaporators, which then required excessive defrosts. There was also issues with the subcooling. All the condensers were on ground level and receivers also below the condenser. There was no subcooling circuits on any of the plants, and all the receivers were at the condensing temperature, so we didn't really have any level of subcooling. We also had a lift up to the evaporators which were at a high level. There was a 10-metre lift to the evaporators, which meant that there was a pressure drop, which meant that by the time the liquid got to the evaporator, unless it was actually subcooled by over 4.3 degrees, we were getting flash gas at the evaporator inlet. We had very unreliable feed to the evaporators, and so we suggested two options, either to fit subcoolers to the liquid line or to fit a liquid pressure amplification system. Also, the condensing temperature could have been reduced quite considerably to 25 degrees centigrade. There was also issues with the evaporating temperatures. The cold stores were all evaporating at minus 10 degrees C. This actually increased the energy used by the compressors and reduced their capacity. Due to the poor superheat control I mentioned earlier, it actually was necessary to run at a very low evaporating temperature to make sure the stores could maintain temperature. It was quite possible to increase that evaporating temperature to minus 4 degrees centigrade. And if you increase the evaporating pressure, also reduce the condensing pressure, the COPs of the refrigeration systems would go from just over 2.02 to 3.6. You can see here this is the impact of improving the evaporating and condensing temperatures and optimizing the defrost. And you can see that we'd reduce energy by between 16 and 36%, depending on how well we actually achieve those options. There was also further options that the compressors were not run particularly efficiently. In many cases, several compressors were run when one or two of the compressors could be run alone, and we looked at running the compressors more fully and more efficiently. And if we did that, there was huge savings to be made, between 41 to 65% reduction in the energy by reducing the number of compressors that were used. So you can see there was a number of outcomes from the audit. We found some quite large energy savings. We could reinstall some of the rapid roll doors, we could look at LED lights, we could improve the refrigeration controls, and we could set some of the temperature settings and defrost controls. If you'd like any further information about the work that's been carried out in IC, and in particular audits, information is available on the IC website, and there's information for end users which gives information on how to apply some of these initiatives, and some example case studies which may give you some ideas of the amount of energy that you could save by carrying out an audit.